All right, we're back with week 5, and this is exam for review for exam 1. This is a problem we're not going to do. So one of the reasons why is because it says plot the response. We're not going to do that type of problem for the exam. So we are not going to bother doing this problem. That could be a homework problem in the future if I were to teach this class again. All right, so let's see. We will work on, this is in a book named Inman, and so we can already see that this might be a log decrement problem just by the way it looks. So the displacement of the vibrating spring mass damper system is recorded on an XY plotter and reproduced in the figure. It says XY, but this is a function of time, so I don't know why they made that. The Y coordinate is the displacement in centimeters. I always hate centimeters. And the X is in seconds. All right, so I guess that makes the XY. Plot the, from the plot, determine the natural frequency. So we got 3 things we're trying to find. They say natural frequency, but you don't know if they mean this or this. I guess we'll get to both. But probably, actually, let me put it this way. It's damped, so those don't really matter as much as the damped ones. All right, so do that. B, find the damping ratio. And then the damped natural frequency. Well, see, there's a go. That's kind of weird. All right. I guess they mean this one. And then that one. I just assumed. I should look at my paper. Let's do that. All right, so first off, we have some data to look at. So we're going to try to get right up in there and right up in there. So I'll decide that coordinate right here. It's kind of halfway through these marks. So we have like 1, 2, 3, 4. So each of these marks is 0.25. There's 0.25, there's 0.5, here's 0.75, and there's 1. So we're halfway between 0.75 and 1. So that must mean we're at 0.875. And up here, okay, so I let me put this up here. All right, so here's a coordinate, and the x coordinate, 0.875. And it looks to me like we're just underneath I guess maybe we're at 0.75. You could make an argument otherwise. And this one, this peak, looks like we're at 4.875. So these are 4 seconds apart. And if we're looking at that, it looks like it landed right. Let's look at the increments. 1, 2, 3, 4, 5. So we're counting by 5s, by 0.05s. So this must be 0.2. All right, so first thing we'll do is get the log decrement of that. And I guess I could just plug in the number. That's what I did. We do the larger number over the smaller number, so 0.75 over 0.2. And we get a log decrement of 1.322. So from that, we can get the second one right here. We can get to part B. And that's going to be 2 pi squared plus del squared right there. So there you go. That's what the damping ratio. We'll put in 1.322 square root of 2 pi squared plus 1.322 squared. And we go 0.2059. And we'll look at this period right here. So the period is going to be between the peaks right there. Right? So right there is going to be tau d. And so that ends up being easily enough 4.875 minus 0.875 So 4. And we'll put some zeros there just to say we cared enough. Omega d is going to be 2 pi over tau d. Or 4. And so we end up with 1.571 radians per second. That could be the answer. Quite often I'm looking at the problem. I think we want to find the mass and the we're told the mass. Oh, right down here. Okay, so here's the other things we have to find. So I didn't write D. I'm sorry, I got distracted here for a second. D, found K and C. I think that's the better question, personally. All right, continuing on from here. So we have this, and maybe I want to. So that really answers this question. So let's go to omega d is equal to omega n times the square root of 1 minus squiggle squared. Oh, I should go back up to this. We answered B. So we have this, and we have here. So we need omega n. So we have to rewrite this and write omega n is equal to omega d divided by the square root of 1 minus squiggle squared. And so omega d is going to be 1.571 divided by 1 minus 0.2059 squared. And if we did that right, we got 1.605 radians per second. And we can take a look, and so that's going to be this guy. They didn't mention what the units were going to be for natural frequency, either the undamped natural frequency or the damped natural frequency. We could leave it right here. We could also divide by 2 pi, which I haven't done. Should have, didn't. So if you have 1.571 and you divide by 2 and you divide by pi, we have 0.25 hertz, which makes sense because we have 4 seconds, so it's just 1/4. Dumb. And take a 1.605 and divide by 2 and divide by pi, and you end up with 0.2554 hertz. So that was actually B N, and I should not have written this part right here. I should have written F D is equal to that right there. Boom, boom. That's just more, regular everyday people think of frequency as being in hertz. It's only when you're using sines and cosines is the circular frequency useful. All right, so we know. Okay, so we have this right here. Determine the spring stiffness and the damping coefficient. And so we'll take our natural. Let's see. It's time for another color. Well, I think it makes life better to have different colors. We'll take this equation, wrap it around, and find K by taking M and the undamped natural frequency squared. So we're told it's 100 kilograms, and that we have 1.605 squared. So we have a mass of 257.7. Oops, not a mass. We have a stiffness. Yeah. And then from this information, we have the critical damping ratio of 2 times mass times natural frequency. So 2 times 100 times the natural frequency, undamped natural frequency. And so we get, that's 321.0 Newton seconds per meter. So we can find orange. Oops, let me get right out the equation that we'll use. So we have squiggle is equal to C over CC. Therefore, C is equal to squiggle times CC. Or the squiggle is 0.2059. CC is, we just wrote it, 321.0. So we get 66.09 Newton seconds per meter. So the answer is black enough is K is equal to 258 newtons per meter, and C is equal to 66.1 Newton seconds per meter. I think that's the more important stuff than these others. So we have that thing going for us, which is nice. And we have a 10-minute, 11-minute problem. That's about what we want to try to have, like a problem that's about probably this complex. So it's a good candidate for a problem for an exam. More soon.